Okay, the first hard derivative we're going to take this semester is going to be the derivative of e to the x. Turns out that the derivative of e to the x is e to the x. I want to give two kinds of answers. One's a fake answer, but it's how someone would have thought of it to begin with. And the other is real and probably mirrors much more what Euler did when he originally discovered it. Let's do this graphically first. It goes very quickly. We know that the graph of e to the x just looks like that. Let's call that y. If I wanted to graph the derivative, let's call that y prime, it's just not that hard. I'm supposed to pick some points. Let's pick that point right there. If I draw the tangent line looks like it has a slope of 1, so we'll do it like that. I'm supposed to pick a point way out here and find the slope. That looks really high. I'm just going to say it's at a very high y value. The slope right here, way to the left, is negative and tiny, so the y values here are negative and tiny. And when you graph this, it looks like you graph something very, very similar. It's certainly exponential, and it's very possible it could be the derivative of e to the x. And it could be e to the x. That's how someone would guess a derivative of e to the x is e to the x. That's not the real way, but that is how someone would guess it. Let's go through a much better method. It's not quite strict enough for a mathematician, but it's pretty close. We do have to recall the definition of e, and we're going to have to change it just a little bit. Definition e. E is what you get when you take 1 plus 1 over n to the nth to very high powers and then take the limit. So you're going to get something like this. When you took algebra, this was the definition because you were just looking at compound interest actually and seeing what was going on. And you can take, Desmos or any calculator you like and start plugging in huge n's, and you get very close to the number they usually use. Now, we're about to take a derivative, and the problem is that derivatives don't have n's going to infinities. They have h's going to 0. So we're going to change the definition just a little bit. I'll probably put it over in the corner and hope we won't get to it too much. What we're going to do is we're going to let h be equal to 1 over n. That way, when n gets huge, h gets small. So what we're going to get here is we're going to get the limit, not as n goes to infinity, but as h gets close to 0 like that. Now, 1 over n is h, so I'm going to get this. I get 1 plus 1 over h. And instead of n, I want that in terms of h. Well, h is equal to 1 over n. That says n is equal to 1 over h. Yeah, I didn't do this right. This is supposed to be h. Here we go. And this is 1 over h, like that. So this is the definition that we're going to use for e. And what I'm going to do is erase the whole board. I'm going to put that over in the corner, and when we need it, we'll have it. So erasing the whole board, we're just going to put this in the corner. Maybe we can see it, maybe we won't. We'll just see. I'm just going to write down that e is what you get when you take the limit as h goes to 0 of 1 plus h to the 1 over h. That's what we want right there. Now, we want to take the derivative of e to the x, but we don't have a formula at all, so we're going to have to use the definition. So the derivative of e to the x, and here we go, it's the limit. And as I promised, as h goes to 0, remember how this works. There's a giant fraction, the h goes down here, the minus goes like that. The e to the x works just like that. And this is going to be e to the x plus h. Now, when we were in chapter 2, we were taking derivatives, we would start doing some algebra, but it's hard to see exactly what algebra we can really work here. You can see that the e to the x plus h and the e to the x both have an e to the x in them. So I'm going to pull it out. And I'm going to pull it really far out because h is the variable here. So I can pull an e to the x all the way out. I get e to the x times what looks to be a horrible, horrible limit. This is just going to be e to the h minus 1 all over h. Remember, that's an h, like that. Now, somehow, some way, we have to figure out that limit. But here's the thing, right? When h is really tiny, e is really close to 1 plus h to the 1 over h. So what I'm going to write is that this e to the x why don't we do it this way? We're just going to say is approximately equal to, and then we'll worry about the limit in the end. Instead of e, I'm going to put its estimate. I'm going to put 1 plus h to the 1 over h. That's just the e part. I'm supposed to be raising that to the h. I'm supposed to subtract 1, and I'm supposed to divide all by h. And this estimate's very good as long as h is very small. Now watch what happens, and this is the idea. This is how you can tell someone like Euler thought of it, because this the kind of stuff he did all the time. When you take a number and raise it to a power, the powers multiply. Well, 1 over h times h is 1, so this exponent just cancels with this exponent. All the hard stuff just went away, by the way. The top of the fraction now looks like 1 plus h minus 1. Well, then the 1's just cancel, right? And now all we have is h over h. Well, the h's just cancel. What we're left with is just e to the x, and there's not even any h's there. And the idea is the smaller h gets, the better the estimate. And if you take the limit, we actually get e to the x. And that is probably how Euler originally took the derivative of e to the x. Just a reminder that Euler is spelled E-U-L-E-R. Yes, that's right. Right, and the reason we call the number E is we're commemorating Euler for that. So there you go. We took the derivative of e to the x, and we got e to the x. So that's actually our first official deep formula for a derivative.